SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 44 on our ongoing series on mechanical measurements. In the last lecture, we have been talking about mostly about gas analysis, and to recapitulate, we had two types of gas analyzers. One in which the constituents are not separated and they are measured in the form of a mixture in which it exists. In the second case, we separated the constituents by a suitable technique and then measured each one of them separately. So, the separation was done by gas chromatograph, if you recall. And the other technique we talked about was differential absorption, which is specific to a particular gas, particular species, which absorbs at one wavelength, and a neighboring wavelength that does not absorb. The differential absorption is able to give us some idea about the concentration. The last one which I am going to describe here is the oxide gas analyzer. In fact, it is one of the earliest gas analyzers which were used in the power plants and so on, and it is a very simple instrument, and it uses, again it separates the constituents into by absorption in a reagent. So, we will look at it in more detail as we go along. Subsequently, I am going to talk about a smoke measurement, which is also important, because we have the smoke or the particulate matter. Smoke is particular refers in particular to the exhaust coming out from engines and so on, but it could also mean particulates in general. So, how to measure particulates in the atmospheric air? So, the issues that will be involved in that is of course collection and transmittance, and one of the instruments which we are going to discuss is the opacity meter. We will describe some ideas about how to collect, and we will also discuss some details of isokinetic sampling. So, to start with, let us look at flue gas analysis. Flue gas means the gas is coming out of a boiler, and the gas will come out through the chimney, and we have to sample the gas at some suitable place and then subject it to analysis. One way of doing that is to use the RSAT analyzer. The name is because of the inventor. It was towards the end of 18th century it was invented, and it is being used regularly in many power stations. So, the principle of operation is very simple. It determines the volume fraction of individual gases in a mixture by selective absorption of the constituent by reagent. Here absorption does not mean absorption of radiation. We are talking about absorption of the species by a reagent. The reagent, when you pass this gas through a reagent or bring it in contact with the reagent, that particular species will be removed by absorption process. So, what is left is the sample minus that particular constituent which is removed, and therefore, by looking at the change of the volume we will be able to find out what is the percentage of the constituent or the volumetric constituents. So, the reagents which are used normally are given here. For example, if absorption of CO2, it is usually 40% solution of potassium hydroxide. For absorption of oxygen, it is chromous chloride, also it is called chromium dichloride. The There are other substances also used, I will come to them as we go along. So, in the case of RSAT analyzer, the instrument is usually made of glass, and the picture shows the photograph of an RSAT gas analyzer, which I have taken from the website of the manufacturers, from the catalog of the manufacturer. So, you can see here that there are several vertical tubes here, which contain actually the reagents, and there is a, on this side you can see a burette, and what is done is a sample is taken in the burette of the gas whose composition we want to measure, and then it is communicated with each one of these reagents in turn, and then it is brought back into the burette and the volume change is measured. I will describe it with respect to a simple two, in this case I have got 4 such reagent columns. I am going to look at one simple example of an RSAT analyzer which has got only 2 columns, and I will just describe how the operation, how it is operated in practice. So, the schematic of an RSAT gas analyzer is shown here. It is taken from a reference which I have quoted there. It is available on the web, and what does it contain? It contains, as you can see here, a long burette with divisions shown on the side, and the volume up to this is about 100 milliliters, and it is surrounded by a water jacket which will keep the temperature constant. Okay. And at the bottom you see that there is a container containing a liquid. In this case it will be water, and this water is the one which is going to be used for either taking the sample into the burette or sending the sample to one of the reagents which are shown here. There are 2 which are shown here. I have taken an example where only CO2 and oxygen are being measured. So, 2 gases are to be determined in this particular case. The lettering here is not very clearly visible, but it does not matter, I will describe it as we go along. So, you see here there is a 3-way valve which can either connect to the atmosphere or to the source of the gas, and then there is an outlet also. Okay. So, it is a 3-way, that means one, it will connect to the atmosphere or to the gas which is being fed into the system which we are sampling, or it to the outlet, so that we can send it away out of the and then there are 2 reagent flasks here, and this is communicated to the burette. Now, imagine how it will work. Is very simple. So, this is the lower level or the 0 level, and when there is no sample in the burette, when it is open to the atmosphere, we can bring the level such that it is in this level. So, the level, this bottle can be raised up and down to change the level of the liquid or the separating liquid, in this case water. Now, if you open this to the source of the gas which we want to sample, what we can do is we can raise the level of this, so that this level goes up to the 100 milliliter mark. The 100 milliliter is the amount of sample which you are going to collect. So, it is going to be raised such that this will be at this level. Therefore, all the gas which is present in this is expelled to the atmosphere first by opening it to the atmosphere, then close the and open it to the inlet port, and then you lower the liquid level to the original level. So, what will happen is that the sample will be drawn into this, because as you move the liquid down, this vacant space which is created will take the sample, and the sample will fill this. Usually the sample is taken 1 or 2 times or 3 times, and then it is sent out of the through the outlet hose, so that we have flushed the entire burette plus the connecting tubes of the atmospheric air which would have been present to start with. So, you first remove all the atmospheric air, and then finally you fill the entire thing with the gas whose concentration of the species in that gas we want to measure. that is going to be filled with that, and this is closed. Of course, during this whole entire operation both these valves are closed. Suppose we want to find out how much is the carbon dioxide by volume which is present, we will communicate it with this particular vessel here, and there is of course a mark here. So, the level of this fluid will be up to this mark, and now what we do is we transfer the gas by again raising this the gas and opening this valve, the gas will be sent into this reagent container, where the carbon dioxide will be absorbed by the potassium hydroxide solution. Okay. So, allow enough time for it to come in contact with the potassium hydroxide by arranging such that this level is going to be at this level. So, that the entire 100 milliliter has gone into this reagent container, and then again you bring it back, and then the gas which has gone into this container will come back into this portion which is here. So, when it has gone into the reagent flask, the carbon dioxide will be absorbed. So, whatever percentage of carbon dioxide is there in the sample will be absorbed, and therefore, what comes out is only the rest of the gas. So, what will happen is that when you bring it down, this level will go to a higher level, and of course, this will also be at a higher level, because the amount of gas which will be now the volume of the gas will be lower by the amount of carbon dioxide which was present in the sample, which has been absorbed by the reagent in this tube, in this vessel. So, you measure you note down the reading here, and that will immediately give you this is 100, this is 0, and this will immediately give you the percentage of volume of the gas carbon dioxide in the mixture. Now, we have to close this and then open this and again transfer this gas to the other solution, the chromous chloride solution, which will absorb oxygen, and then again do the same operation of bringing it back to this vessel or to the burette, and then you will see that there will be a further reduction in the volume, and the difference between the previous reading and the the subsequent reading will give you the percentage of oxygen by volume. So, in this case I have taken a case of Rarsat analyzer with just two of them, one for carbon dioxide, one for oxygen. So, this will give you an idea about how much is the carbon dioxide percentage by volume and how much is the percentage of oxygen by volume, all at a constant temperature, because this entire thing is going to be surrounded by a water jacket at a constant temperature. So, this is at the constant temperature, the percentage by volume will also be the molar percentage, as we already know. So, it is a very simple instrument, and let us look at what are the possibilities. We are talking about very small values of the percentage of carbon dioxide. Oxygen will be very small if the combustion in the furnace, the boiler furnace is more or less complete. The amount of oxygen will be very small. In fact, this can be used for finding out how much excess oxygen is there, because whatever oxygen is not used in the combustion process is going to be present. Secondly, the carbon dioxide percentage will give us an idea about how much of carbon dioxide has formed in the reaction which has taken place in the combustion process. The third point I would like to say is that because the fluid which is going to be used for in the liquid contained here is water, what will happen is the entire manifold here and the burette and so on will be fully saturated with water vapor, because there is enough water available for that, and therefore, the measurement is on what is called dry basis, because we are not taking into account the moisture which is going to be present, which is always there. So, even if moisture is present in the incoming gas which we are going to measure in the sample which we are going to measure, the water vapor, water concentration is not going to be affecting the measurement, and therefore, we call the measurement as dry basis. So, we have more or less completely looked at the measurement of gas composition. Several methods have been considered, and let us now look at the other important problem, which is important from many points of view. One is of course the atmospheric pollution point of view. Soot, smoke and such particulate matter always give us problem, because they have implications for the health of the people, and also the visibility of the atmosphere is significantly affected by the presence of these particulates, and it will affect the the operation of aircraft and things like that. There are so many different ways it can affect. It can also affect the weather because of the particles may create adverse conditions from the point of view of absorption of solar radiation and things like that. Sometimes the particles also come back to us as acid rain. That is one of the major problems, and this acid rain is because of the gases which are present in the atmosphere, which for example sulfur dioxide and nitrogen, oxides of nitrogen and so on, which are produced in large amounts by power plants. These go out in the atmosphere, they form particulate matter because of reactions with some suitable materials available there. Then you have particulates. These particulates also are hazardous, and they have to, so we have to monitor the amount of particulates which are in the atmosphere. Therefore, from this point of view, it is essential to know how to measure the particulates. So there are several possibilities, and I am just going to look at one or two. So the first thing I am going to look at is the measurement of soot or smoke. Soot and smoke literally they do not mean two different things, they are more or less the same thing, just the proper diameter of the particle which tells you whether it is a soot or a smoke. So in any combustion process, for example if you take a diesel engine, the exhaust contains a lot of smoke, and you can very well see that it is because of the incomplete combustion of the hydrocarbon, and therefore the unburnt carbon remains as particulate matter or particles, and these come out of the tailpipe of the car. If it is a automobile, or if it is a regular power plant, it will come through the stack. So there are two things which are involved in this, two general ways of measuring the amount of soot or smoke. One is to measure by collecting the particles by a suitable method, and then either you can do weighing the particles or measuring the transmittivity of a collector on which the particles are deposited. We will look at that as we go along. The other method is to measure what is called opacity, and this can be measured in situ, that is you do not have to collect a sample, the in situ measurement is possible. For example, in the case of a smoke stack, the stack itself, the instrument opacity meter can itself be mounted on the stack itself, so that directly the measurement can be done in situ. So the advantage is that it can be monitored in real time, whereas in the case of collection you have to collect the sample, and it will take some time to collect the sample and then do the measurement, either weighing or opacity measurement. It has to be done separately. Therefore, if one is interested in measuring in real time and monitor what is happening in the smokestack, the best method is to use a opacity meter. Let us look at the type of things we are talking about. I have taken a simple example of diesel particulate emission. So this is from the reference which is given here, polarized light scattering measurements for sizing diesel particulates by Hunt et al. So it is the material is available on the web, and I have just downloaded this figure from their from the web, and what it shows is that the percentage of total number of particles and the diesel particle diameter. It just gives you what is called the particle diameter distribution. That means that the particles are all not of the same diameter, they have different diameters, and there is a distribution. But in this particular example, what they did was they were running a Cummins diesel V590 engine, and then the exhaust was taken from the engine, it was diluted by in the ratio of 5:1, so that the concentration of the pollutant is brought down, or the smoke concentration has been reduced, so that it can be measured easily, and then it was operated at full load and 1600 rpm, that is the speed of the engine, and the mean diameter of the particles, as you can see, is 30 nanometers. So the particle diameters are very small. So that is why I said in the beginning, the smoke and soot, the difference is only in the size distribution of the mean diameter. In this case you can see that the mean diameter is 30 millimeter, will correspond to some value here. This is 0.05, so 0.03 is where you have to have. So this is given in scale of microns, and therefore 0.03 is somewhere here in this portion. So you can see that the maximum concentration occurs somewhere close to that value, close to this value 30, maybe a little smaller than that, and the really large particles are very small in number. So, most of the particles are within 0.2 to 0.25 micrometers in size. So, this just gives us an idea as to what we are talking about. When we are talking about diesel smoke, when you want to monitor the smoke amount of smoke in the tailpipe of an automobile, we are talking about particles of such diameter and such distribution. So, what are the issues involved in this measurement? So, as I said, we can have two different ways of doing the measurement. One is to collect the particles. So, the particles have to be collected by sampling the gas by using a sample probe, and we will describe how that has to be done. So, what are the requirements of that, and also we must note whether there is any particle losses in the sampling tube because of settlement. For example, if you have a horizontal tube and you are sampling a gas containing some particles, the particles can settle down because the particles are heavy with respect to the gas molecules, and therefore, they have a propensity to settle down in the gravitational field. Or if you have, for example, a tube which is, or the probe is angled, or it is not a straight tube, but a bent tube, wherever there is a bend, the gas will have to go through a change in direction, and at that time there will be centrifugal forces, and therefore, in the centrifugal force field the particles will, because of inertia, they will go straight rather than take the bend, and they will hit the other side of the wall of the probe tube, and they will settle there, they will adhere to the surface. Therefore, these are some of the issues one has to be careful about while sampling. The sampling is not very simple, there is some amount of thought has to go for that. Then there is what is called isokinetic sampling. This is an important concept. So, before collection and weighing the sample, weighing the particulates, we have to do what is called isokinetic sampling, and it can be simply mentioned in the form of following two statements. Sample probe should be aligned parallel to the gas stream, that is very important. So, it should not impinge, the gas stream should not impinge on the side of the tube, because as I mentioned, the particles can settle down on the sides of the tube, and the gas velocity entering the probe should be the same as the free gas stream velocity. This is very important. So, the two requirements are, there should be no hitting of the gas stream onto the wall of the probe tube, and the second, the gas velocity must be the same as it enters the sampling tube. Why do we require that? We require that because otherwise it will be not isokinetic sampling, and therefore, there will be change in the concentration which is measured. The measured concentration and the actual concentration will not be the same, as we will show you in a few minutes from now. So, what are the particle loss mechanisms? I have already mentioned in passing just a while ago. One is inertial losses in a curved tubes due to centrifugal force field, and the second is gravitational losses in horizontal sampling tube due to settling of the particles and the action of gravity. Of course, under action of gravity, the particles tend to come down, and of course, viscosity of the gas will tend to impede that progress, and therefore, what happens when particles are trying to settle down in a gas stream is that they will achieve what is called a terminal velocity depending on the viscosity of the medium, in this case of course air. So, they will have a terminal velocity, and because of that it will come down and settle down. And in fact, if you have the vertical orientation for the sampling tube, these losses certainly can be reduced or eliminated. So, isokinetic sampling involves the following. Let us look at what is called the Stokes parameter. This plays an important role in this. The Stokes parameter STK is given as tau. Tau is called a particle relaxation time. I will just tell you what it is in the next slide, multiplied by the velocity of the gas stream u subscript 0. This is called the free stream velocity. U naught is the free stream velocity, and the diameter of the sample probe is in the denominator. So, this Stokes parameter, if it is less than 0.01, sampling is expected to be isokinetic. Therefore, if you want to find out what kind of a diameter of the sample probe to use, then we have to find out the value of the Stokes parameter and find and make sure that it is less than 0.01, so that isokinetic sampling can be achieved. So, the variation of relaxation time with particle diameters is given here. This is based on experimental data, and I have taken it from the reference which is shown here. It is a manufacturer's reference. They have given this in their technical note number 2 as is given here, and the particle relaxation time depends on the diameter of the particle. This is not the diameter of the sampling tube. I am now talking about the diameter of the particle, and if you remember, the diameter of the particles were given earlier in the case of Cummins engine. We had the diameter varying over a certain range. So, here we have taken the normal range of diameters which are useful in practice, and I have gone from 0.1 to 10 micrometers. These are very large particles and these are relatively smaller particles, and this is the kind of particle we talked about when we were talking about the diesel engine. So, you see that the relaxation time is very small, about 100 about 10 nanoseconds here, and then progressively here it is about 1/10 of a millisecond. So, for very large particles the relaxation time, this relaxation time is something to do with the isokinetic sampling. We require that Stokes parameter to be less than 0.01, and this relaxation time goes into that formula. And let us look at a typical example, typical type of situation which will prevail. Suppose we have the Stokes parameter is given here, and the particle concentration in the sampling tube is what you are going to measure, and the C naught is the particle concentration in the free stream, which is what we would like to measure, and if the velocity in the sampling tube is u, you see that there is a this C by C naught equal to 1 would correspond to isokinetic sampling, but there is a correction here where it is u by u naught minus 1. This will be a negative quantity if u is less than u naught. Of course, u could be greater than u naught if you have a acceleration of the gas stream when you collect it, and then you have another correction factor which involves u by u naught as well as the Stokes parameter. So, general formula is this. Based on this only we have given the requirement that Stokes parameter should be less than 0.01 for isokinetic sampling. So, let us take an example just to see what the numbers are. I am taking a simple case of a mixture of the various diameters are present, and let us assume that the largest diameter of particles which are present is 10 micrometers. Okay. So, we want to determine the diameter of the sampling tube. The largest particle diameter is expected to be 10 micrometers, and the other pertinent data is u naught is 2 meter per second, that is the mean free stream velocity, and I want to make sure that the flow rate through the sample tube is not less than 100 milliliters per second. So, this is important. So, we will work out, we will see how to design the diameter of the sampling tube. So, on the board I will show that. So, before we take up this example, let me just describe how it is done. So, you have a tube, this is the sampling tube, and of course, the stream is coming here. This is the particle or dust laden stream, which I am calling as the free stream. So, why will the gas go into this tube? So, I have to aspirate or suck it out by some suitable means. So, we have to have a suction device, that means that you have to make sure that there is some positive, where there is a pressure gradient available, so that the stream will enter this. So, what I want to do is I want the stream to enter with the same velocity. This should be u, this is u naught, this is u, I want u equal to u naught, because that was the requirement. Therefore, the tube shaping has to be such that this can be guaranteed. Therefore, you may, first of all we are going to aspirate, and then of course, when you aspirate it may be too much flow or too little flow, you may have to control it with along with a valve, a control valve, so that we can control the velocity. So, the velocity in the tube will be monitored and the aspiration rate and the suction rate will be adjusted such that velocity is equal to u naught. So, this is one part. The second part is that we have to have tau, the Stokes parameter less than 0.01. These are the two things. In this case, we are given that the velocity u naught is 2 meter per second, and then for the 10 micrometer particles tau, this is for dp equal to 10 micrometers, fairly large size particles. Tau is given as 3.11 into 10 to the power of minus 4 second, almost 0.3 millisecond. So, I can find out the Stokes parameter, if you remember, is given by tau u naught by ds, where ds is the sampling tube diameter, tau u naught by ds, and this should be less than 0.01. So, what I will do is I will assume I know the value of tau, I know the value of u naught. Now, I can find out ds by simply plugging in the numbers. So, we will say ds, if I take it to the other side, should be greater than tau u naught by 0.01, and I can put the values 3.11 into 10 to the power of minus 4 into 2 meter per second divided by 0.01, and this comes out to 0.0622 meter. Okay. That means that the sampling tube must have a diameter greater than 0.0622 to satisfy the one of the requirements of the isokinetic sampling. The next one, we are also told that we have to have a volume flow rate not less than, that means it should be greater than 100 cc per second or 100 milliliter per second. So, now I will find out what is the requirement of the diameter of the thing, because we know that the velocity is equal to 2 meter per second. Therefore, this volume flow rate, if I call it as q, q is nothing but pi ds squared by 4 area times the velocity u, this should be greater than 100 milliliter per second. So, I can find out ds, therefore, should be greater than 4 into 100 divided by pi will come from the multiplied by u square root of. So, I can again plug in the values. This will give you 4 into this 100, I should convert it to the SI unit. So, what I will do is I will just put it as 100 into 10 to the power of minus 6 cubic meter divided by pi into u is in 2 meter per second. This will give a value of 0.00798 meter. So, we have two values now. The first requirement from the Stokes parameter value for consideration is that the diameter should be greater than 0.0622. I think it is 0.00622. Okay, we will correct it here. And from the point of view of volume flow rate, it is 0.008 meters. So, this is a 8 millimeter tube and this is a 6 millimeter tube. So, we would have to choose this, because the larger, because this requirement is more important than this requirement now. Therefore, we will be having a diameter equal to, so ds is chosen as 0.008 meter or 8 millimeters. So, the diameter of the tube at least must be either 8 millimeters or even more, because 2 meter per second, that velocity is constant. Therefore, 100 milliliter second per second will flow through that, but it should be, there is a lower limit. So, it could be more, that means that I have to choose a diameter of 8 millimeters or more. In this case, if you want to work at the limit, we can just take a value of 8 millimeters for that. So, we have some idea now about the isokinetic sampling, and let us look at the what we can do with it, what we can do with the sampled gas. So, let us look at the possibilities. One possibility is to do the following: to collect the particulates only. For example, if I have a filter paper, or some material, and I am having the gas plus particles, so the gas will pass through and the particles will deposit. So, particles get deposited on the filter paper. Of course, filter paper means it could be some filtering element. Let us filter paper can also be used, one of the possibilities to use filter paper, but if the diameters are very small, filter paper will not do that. Then we will have to go for a suitable material, and usually they are called molecular sieves. That means that the gas only will pass through, and the particles, even very fine particles, will deposit on the filter element. So, we can say filter paper or filter element. These filter elements are usually made of material which will withstand the type of situation which we are having here. And what can be done is, there are two ways of using this. One is to, of course, weigh the filter before and after. Before and after collection. Before collection, we know the weight of the filter element, and then after collection we find out what is the weight of the filter element, and then the difference must give the amount of material which has collected. Now, the point is, if you want significant amount of material to be collected so that you can do an accurate measurement of the mass, we require a large amount of time. For example, in typical cases it may be about 24 hours. So, you collect the material for about 24 hours, and then you have to start with, you have weighed the filter element, and after enough material is collected over a period of, let us say, 24 hours, we can weigh it, and we can then find out how much of the gas has passed through the system. So, in 24 hours, what is the total volume flow? This is easy to measure, because we know the velocity of the fluid in the sampling tube, we know the area of cross section of the tube, and we know the amount of time for which we have held it, which have conducted this collection of the particles. We can actually find out the total volume flow, or you divide it by the number of seconds or hours during which you have collected, you get the rate at which the volume flow is taking place. So, volume flow rate, total volume flow, or the volume flow rate. One or the other. So, total volume flow you know, and then you find out what is the total amount of material connected. So, if the weighing gives you the amount in milligrams or micrograms or whatever, so mass collected divided by the volume flow, which we will call it as total volume flow, will give you the So, mass milligram per, for example, meter cube, that is what we want. So, this gives you the concentration, this is another word, the concentration of the smoke, concentration of the particulates. If it is smoke particles, we can say it is smoke concentration. If it is dust, for example, which is present in many industries because of industrial activity, because the process involves a lot of powder materials and so on, this could be also the concentration of the dust particles. You collect the dust through a filter element, weigh it before and after, and then you find out what is the volume flow rate of the fluid, gas which has passed through, and then you divide one by the other, you will get the concentration of the dust particles. So, either the dust particles can be the concentration of dust particles, or in the case of smoke or soot, it is the soot concentration which we are going to get out of that. So, let us look at the another way of doing it. So, another way would be the following. So, you have collected the sample or the filter element, and I can measure the optical transmittance. In fact, there are many other interesting ways of doing it. I will just give them in some detail. For example, you have the dust particles or the soot particles have been collected on the filter element. We can compare this visually with a sample of known density of particles deposited on another filter paper, which can be taken as a reference. So, if you have several references with different amounts of the dust particles being present, I can just compare and find out which is closest to that visually, and immediately say that this is like this particular concentration. So, that is one possibility, that is by comparison with a standard concentration which is obtained by comparing with a standard. The second one is to measure the optical transmittance before and after. That means that you have the filter element without any deposition, you find out what is the transmittance of that for optical or that is visible light of some suitable wavelength or frequency, and then after the deposition has taken place, you find out what is the change in the transmittance. So, that can be another way of measuring. So, this is second way of doing it. One is already I said weighing, first one. Second one is measuring the optical transmittance of the filter element. So, this measurement is also actually called opacity measurement. This measurement is called the opacity measurement. So, what we will do is, opacity measurement can be done in this case also, but what I will do is I will describe a opacity measurement in the in situ case, because there we are not collecting the material. Here we have a filter element, and you can just what you do is you put the filter element in the path of a light beam, find out what is the transmittance before and after, you get the opacity. But this opacity is now related to the total amount of material which is collected over a given amount of time, and therefore, you have to relate it to the concentration of the dust or the gas particles or the particulates in the original gas sample by using a little bit of algebra. The other method is in situ measurement. Which again uses opacity measurement, but not opacity of a filter element, it uses the opacity of the gas itself, opacity of the particle laden gas. So, this becomes in real time. This is not real time, because this is going to be over a long period. In a way, this also gives you the average or the mean value whereas this gives you the instantaneous value in real time or instantaneous value. So, what is the difference between these? Let us look at that instantaneous value. Mean value means over a period of 24 hours, for example, you are collecting the sample or collecting the sample on the filter element. Throughout the 24 hours, it may not have been exactly the same concentration. Concentration might have varied. Sometimes the concentration might have gone up, sometimes it might have gone down. So, what we will get over a 24 hour period, what is the mean value is what I can get from this. But supposing I want to know what is the rate at which it is produced over a period of time and how it varies with time, I can only do by the in situ measurement. So, the in situ measurement is useful when you want to do it in real time. Let us look at that in some more detail. So, for that we are going to use what is called a smoke opacity meter. I will just briefly, this is just the appearance of an instrument of that type taken from the manufacturer. Manufacturer himself is called Preferred Instruments, is the name of the company which makes this smoke opacity meter. So, it consists of a transmitter of light. I will describe more fully the details, and then you have a receiver, and in between these two stations you must have the gas which is having particulates will pass through. So, the light which is leaving this source gets attenuated because of its passage through the dusty atmosphere or the smoke, and then it is measured by this receiver, which usually is a photo detector, and by measuring the amount of light leaving here and what is received here, we can find out what is the opacity of the intervening medium, and of course, we know what is the length of the travel of the light through the particle laden or smoky gas. So, this can be, for example, this can be connected right at the exit of the chimney or the stack, and you can measure the concentration in situ. So, before we take up that problem, let me just describe some of the issues in that. Before we do that, let us just find out what is how we define the opacity, the new terminology. Opacity is nothing but, we will call it O for lack of any other symbol. So, it will be 1 minus light transmitted divided by light emitted by the source. That is what I am thinking of is I got a source of light here, so let us assume that the intensity of light is I, and I have the receiver here or the detector. This is the photo detector, and the path length is L between the two stations, and what is reaching here is I t. So, this is your I t, and this is your I which is leaving. So, opacity is nothing but 1 minus the light transmitted divided by light emitted. So, 1 minus that, in other words, this is what is available at the end at the photo detector. That means that much has reached this place. So, this is the transmitted amount. It is nothing but the 1 minus the transmittance. So, we can also define it as 1 minus tau, 1 minus transmittance. So, we will say it is also equal to 1 minus transmittance. So, what is measured is this, the ratio of these two, and then you find out what is the opacity, and opacity can be a measure of the amount or concentration of the particulates. How does it come about? Let us look at the relationship between IT and I, we have already come across this earlier. This is given by exponential according to the absorption and the scattering of the particles. Because of the absorption and scattering, it will be the intensity will be reduced, and this ratio is given by exponential of minus beta times L, where beta we call it as the extension coefficient. We have already come across this law, which we call as the Beer's law. Okay. So, this extension coefficient beta is due to two reasons. One is absorption and the second one is due to scattering. So, these two together is the reason for reduction in the amount of light reaching the detector. That means that the IT is less than I because of absorption by the medium and the scattering in the medium. Let us also look at the formula which I gave earlier, minus beta. This L also is important. This is the length of travel through the sample. At the length of the or the path length. So, beta times L. So, the unit you can see e to the power of minus beta L, extension coefficient must be 1 over length in unit, because e to the power of I cannot take a exponential of a dimensional quantity. Therefore, beta has units of meter to the power of minus 1. L is meters, beta is in my meter inverse. We can also we can, if we know, for example, if you know the properties of the particles that are present, like its absorption and scattering properties, then I can find out how many particles are there, what is the particle density and so on. These are all possible, but that requires a lot of information. It becomes, it is not easy to do that, it requires a lot of information. And let us look at the type of arrangement we are going to have, which I think I should mention. What we in the measurement is made, or opacity measurement, using the light from a LED. LED is nothing but a light emitting diode. And the wavelength which is used is between 0.55 and 0.57 micrometers. This is the lambda of the light which is being used. It is the visible part of the spectrum. Okay. So, we use lambda equal to 0.55 to 0.57 micrometer, and receiver is a photo detector. And what will happen to the beam is, the beam is a collimated beam with a spread with beam divergence around 4 degrees, less than 4 degrees. It normally, that is the specification for the one which I showed, the photograph I showed. Actually, beam divergence is less than about 4 or 5 degrees, and the accuracy of the opacity measurement is plus or minus 1%, and the calibration drift is less than about half a percent, less than about half a percent. So, we use a specific wavelength, therefore, this is very important to remember. If you use a different wavelength, the properties of the medium will be quite different. Therefore, when we are comparing or when you are quoting the numbers, one must immediately see which instrument has been used, what is the wavelength which was used in that particular instrument, and so on. That is very important, because opacity is not independent of the wavelength of the source of radiation. If you use, for example, if you use a laser, helium neon laser for example, which has a higher wavelength than what I have given here, it will give you a different opacity. One can use that. In laboratory practice, we might use a helium neon laser instead of a light from a LED. In the case of light from LED, you require a lot of optical elements, because you need a lens, focusing arrangement, and so on, so that you get a 4-degree divergence, less than 4-degree divergence, and then of course, you have to collect the signal at the photo detector by using a suitable optics. Or another possible method is a single ended instrument. The one I described above is a 2-ended means double ended instrument. The single ended means transmitter, receiver at the same position. So, in this case what we do is, we will be having what is called a retroreflector. So, you have the transmitter, receiver, and then it goes here, and we have essentially a mirror. So, we call it a retroreflector. Retroreflector is one which will reflect it back in the same direction independent of the incident direction. Whenever it will go back in the independent of the orientation retroreflector itself, it will go back. So, the forward beam and the backward beam, they are just retracing the path. There is there are two advantages. One is, if this is L, this is also L. So, 2L is the path length. So, we get an advantage in terms of the amount of path length available, and therefore, it passes through the gas sample twice, and therefore, the optical path length is increased. And of course, the transmission and receiver is done at the same place, and therefore, you can have all the measuring part, the electronics can be at one end. Everything can be at one end. So, that is the advantage of this instrument. So, what we will do is, we will try to look at a typical case and look at example number 50 in the next lecture when we come back. So, thank you very much.